Welcome to today's Explainer. We're doing something a little bit different today. We're going to look at the chemical world, but not just as students. We are putting on our detective hats. Our mission? To uncover the hidden, microscopic transformations that are happening all around us every single day. I am absolutely thrilled to guide you through this, so let's jump right in.
Think about this for a second. What do digesting your lunch, a rusting iron pan left out in the humid air, and fermenting grapes all have in common? You might not really think about them as being connected, but these everyday mysteries all share one core secret. They aren't just random occurrences. They're actually chemical reactions happening right under our noses where the fundamental identity of the starting materials completely changes into something new.
So, here's our roadmap for this explainer. We'll kick things off by learning how to spot the clues of a chemical reaction. Then, we'll cover the shorthand for writing chemical equations, followed by the golden rule of balancing them out. Finally, we'll categorize our chemical suspects into a few specific types of reactions.
All right, let's get into part 1, identifying chemical reactions.
Every good detective needs to know when a chemical crime has actually gone down, right? We need concrete evidence. Take the burning of a magnesium ribbon, for example. When this happens, it burns with this incredibly dazzling, brilliant white flame. But more importantly, the identity of that ribbon changes entirely. It goes from a solid strip of metal into a crumbly white powder called magnesium oxide, all because the magnesium is reacting with the oxygen in the air.
So, how do we know for sure that a chemical reaction actually occurred, and it's not just a physical change? Well, we look for 4 unmistakable clues: a change in state, a change in color, the release or evolution of a gas, and a change in temperature. Honestly, if you spot any of these signs, you can be highly confident you're witnessing a chemical reaction firsthand.
To really see this in action, let's look at a classic lab experiment. Imagine dropping zinc granules into a flask of dilute sulfuric acid. Almost immediately, you'd see bubbles furiously forming around the zinc. That's hydrogen gas being created. And if you were to actually touch the outside of that glass flask, you'd feel that it's gotten quite warm. So right there, we have a temperature change and the evolution of a gas. 2 massive clues that our suspects are actively reacting.
Moving right along to section 2, how to actually write these chemical equations down.
Once we've observed a reaction, we have to write up our detective report. But let's be honest, writing out long descriptive sentences is just way too tedious. A word equation like magnesium plus oxygen yields magnesium oxide is clear enough, but it's pretty clunky. So we use elemental symbols from the periodic table to transform that sentence into an elegant, concise chemical equation. Mg plus O2 gives us MgO. It's a scientific shorthand that is just infinitely more useful.
Let's make sure we've got our vocabulary straight here. The substances that actually undergo the chemical change, like our magnesium and oxygen, are called the reactants. They always sit on the left-hand side. The totally new substance that gets formed is the product, sitting on the right-hand side. And right in the middle? An arrow. That arrow acts like a one-way street sign, pointing directly towards the newly formed product to show us exactly which way the reaction is flowing.
Okay, on to section 3, balancing the equation. This is where things get really precise.
Our detective work here requires us to keep the chemical scales perfectly balanced. Why? Because of an absolute fundamental rule of the universe, the law of conservation of mass. Mass can neither be created nor destroyed in a chemical reaction. Basically, the universe doesn't do magic tricks. The total mass of the elements you end up with has to be exactly equal to the total mass of the elements you started with. The atom count must be identical before and after.
To make sure everything adds up, we use a process called the hit-and-trial method. It's actually pretty simple. First, you mentally or literally draw boxes around each chemical formula. This is your strict reminder. Absolutely do not change anything inside those boxes. Next, list out the number of atoms for each element on the left and right sides. Finally, you just start balancing, usually picking the compound with the maximum number of atoms first. Just take it one step at a time.
Let's look at an unbalanced suspect equation, iron reacting with water. When we list out the atoms, things are clearly out of whack. We have 1 iron atom on the left, but 3 on the right. 1 oxygen atom on the left, but a whopping 4 on the right. Our scales are completely tipped. In chemistry, we call this a skeletal chemical equation.
But watch what happens when we step in and apply our multipliers. We balance the oxygen by putting a 4 in front of the water on the left. Now that throws our hydrogen out of balance, giving us 8, so we fix that by putting a 4 in front of the hydrogen gas on the right. Lastly, we balance the iron by dropping a 3 in front of the Fe on the left. And bam! 3 iron on both sides,
8 hydrogen on both sides, 4 oxygen on both sides. Perfect harmony.
Now, to make our report totally bulletproof, there's one last detail. We add these tiny letters in parentheses next to our formulas to show the physical state of each ingredient. We've got S for solid, L for liquid, G for gas, and AQ for aqueous, which just means it's dissolved in water. This gives us the complete picture of what form these chemicals were in when the reaction went down.
Section 4. Combination and exothermic reactions. Let's start categorizing.
Now that we know how to log our findings, let's group our suspects based on their behavior. First up are reactions that just love to come together, combination reactions. The definition here is super straightforward. It's when two or more reactants combine to form a single unified product. Think of it as the ultimate chemical marriage, where multiple separate pieces merge into one whole.
A great example is what happens when you mix calcium oxide, which you might know as quicklime, with water. They react incredibly vigorously, combining to form a single product called calcium hydroxide, or slaked lime. What's really cool is that this slaked lime is historically what people used to whitewash walls. It slowly reacts with carbon dioxide in the room to give the walls a really nice, shiny finish.
But here's the kicker. If you were holding that beaker of quicklime and water, you'd notice something else right away. It gets really, really hot. That makes it an exothermic reaction. Basically, heat is released right alongside the formation of the products. And exothermic reactions are happening all around you. Breaking down your food into glucose for energy, exothermic. Vegetable matter decomposing into compost in your backyard, that's a wonderfully warm exothermic process too.
And finally, Section 5, decomposition reactions.
So, if combination reactions are all about coming together, decomposition is the exact opposite. This is the great chemical divorce. A decomposition reaction is where a single complex reactant breaks down into two or more simpler products, or splitting things apart.
Thermal decomposition is a perfect example of this. Picture heating some green ferrous sulfate crystals over a lab burner. As you apply that intense heat, the single compound starts to break down. The crystals lose their water content, turning a brownish color as they become ferric oxide. At the same time, it releases sulfur dioxide and sulfur trioxide gases. If you were in the room, you would literally smell the sharp, unmistakable odor of burning sulfur.
But heat isn't the only way to break things apart. Sure, heating lead nitrate powerfully decomposes it, releasing these thick, toxic-looking brown fumes. But what if we just leave some silver chloride sitting in a simple dish in the sun? Just exposing it to sunlight provides enough light energy to decompose the white silver chloride into gray silver metal and chlorine gas. In fact, this exact light-triggered decomposition is the literal magic behind old-school black and white photography.
So, as we wrap up this explainer, I really want you to take a look around. You are now officially equipped with the clues. You know to look for changes in state, color, gas, and temperature. You understand how elements combine, release heat, and break apart. Knowing all of this now, what hidden chemical reactions are silently transforming the world around you right this very second? Take these new detective skills out into your day-to-day life and start observing. Thanks so much for joining me, and keep exploring.